Vertical takeoff and landing aircraft face a fundamental engineering conflict. Hovering requires pushing massive volumes of air directly downward. Efficient forward flight requires cutting through that same air horizontally, relying on wing surface area to generate lift. Traditional hybrid aircraft attempt to bridge this gap by physically rotating their motors, but tilt-rotor mechanisms require heavy servos, intricate wiring, and complex moving linkages. In continuous operation, every moving part represents a potential point of failure. This is the SP7007, also known as the Genot, an 8-kilogram maximum takeoff weight drone that abandons the tilt-rotor concept entirely. It is designed for a specific operational profile, long-range topographical mapping, and heavy payload delivery in remote, infrastructure-poor environments, like the Himalayas. To address the conflicting demands of hovering and cruising, the SP7007 eliminates articulating parts. Instead, it decouples its thrust vectors, assigning dedicated hardware to each phase of flight. This utilizes a 4+1 architecture. 4 independent vertical motors mount on twin booms for multi-rotor lift. At the rear, a single pusher motor handles fixed-wing cruising. The orientation of all 5 motors is permanently fixed, with no rotating arms or articulating the cells. While this layout simplifies the mechanical hardware, it shifts the engineering burden to the software. The mid-air transition between a vertical climb and a horizontal cruise requires precise orchestration. During this phase, the flight controller must manage power delivery across 2 separate propulsion systems. It has to ramp up the rear pusher motor while tapering off the 4 vertical lifting motors as the wings take over the aerodynamic load. Success in a 4+1 VTOL is less about mechanical linkages and more about the integration of avionics and flight control software. The physical foundation of the SP7007 is a rigid airframe constructed from balsa wood and aluminum plastic film. The aluminum booms are selected to handle the opposing torsion stresses of vertical lift and forward acceleration. The vertical lift is generated by 4 240 kV T-motor MN501S motors, which are optimized for static thrust and hover efficiency. Forward propulsion relies on a single Turnigy G60 pusher motor. Powering 2 independent motor groups creates an electrical bottleneck. A central glass fiber power distribution board routes current from a 6S 8000 mAh battery, acting as a splitter to 4 60-amp VTOL speed controllers and one 75-amp fixed-wing controller. This distribution board serves as the physical bridge, allowing one power source to support 2 completely different flight profiles. Managing that power requires a robust central processor. The SP7007 utilizes a PX4 Cube Black flight controller, paired with a HERE2 GNSS module. The GNSS module provides a 10 Hz navigation update rate and houses an integrated ICM-2948 compass and inertial measurement unit for spatial awareness. However, once the drone transitions to horizontal flight, a standard multi-copter sensor package is insufficient. While a GPS receiver can calculate ground speed, it cannot measure the actual flow of air over the wings. This requires a digital pitot tube. Airspeed data flows via a 4-wire I2C cable to the PX4, determining when wings generate enough lift to cut vertical power. This data loop prevents the aircraft dropping below its 14 meter per second stall threshold. Simultaneously, an RFD 900 Plus telemetry modem maintains a constant 1-watt data link with the ground station. The PX4 must constantly fuse data from these 2 different sensor paradigms, interpreting GPS coordinates for hovering and aerodynamic airspeed for cruising. Hardware is only as useful as its software baseline. Before flight, the PX4 firmware must be calibrated using the Q ground control application. This animation illustrates the spatial calibration sequence. The drone is physically rotated through its pitch, roll, and yaw axes to lock in the accelerometer and magnetometer offsets. For a VTOL aircraft, the digital pitot tube also requires a specific zeroing procedure. The operator must physically shield the sensor from ambient wind to establish a stable, zero airspeed baseline in the software. With the sensors calibrated, the radio control inputs are mapped through a FlySky X8R receiver. The critical input here is the VTOL transition switch. Toggling this specific channel is what commands the PX4 to crossfade between multi-rotor and fixed-wing modes. This calibration process is what integrates a disjointed collection of motors and sensors into a unified, phase-aware aircraft. Once calibrated, the drone can execute beyond visual line of sight missions entirely autonomously. This interface view from Q Ground Control shows the creation of an automated survey. The operator defines a polygonal area, and the software generates a precise zigzag flight path to ensure complete coverage. The mission parameters dictate the exact flight path, locking in a cruising altitude and a target forward speed between 18 and 20 meters per second. During the flight, the RFD 900+ modem broadcasts the drone's status back to the operator in real time. The raw signal is parsed into actionable metrics on the ground station, tracking the altitude, ground speed, and the heading to each specific waypoint. This real-time telemetry confirms the flight controller is successfully managing the navigation logic and transitions under real-world conditions. To protect the aircraft during autonomous flight, the PX4 firmware utilizes mandatory failsafes, automated logic gates that trigger when manual pilot override is impossible. This logic tree maps the data link loss failsafe. If telemetry drops, the autopilot triggers return mode or land mode. Similarly, the low battery failsafe monitors voltage, reserving enough power to transition from forward flight, re-engage vertical motors, and land. These failsafes execute without human input, relying on the accuracy of the sensors and the flight controller's internal logic. The SP7007 demonstrates how a decoupled 4+1 hardware layout and the PX4 ecosystem provide a structured framework for complex, long-range aerial logistics. By shifting complexity from mechanical moving parts to software-defined phases, the system handles the specific demands of hybrid flight.